All right, guys, before I forget what I tend to forget, let's get into part 4. Everything now is smooth sailing because of functions. Let's go back to one variable. Right? And let's write down these names. And one word that I want to emphasize is that these F's, all of these F's are called relations. I've noticed that the same word, relation, is used for these guys as relational symbols. Right? Relate. A function is a relation. It's a relation. It relates your choice or choices if you've got more than one, independent. By independent, it means no one tells you what to choose. You choose. You choose according to yourself. Independently, no one tells you what to choose. The prescription of a function, to say f of x, that is to literally specify your independent choice. Well, in this case, because I've gone back to one function, so I have to, so I can retain that this z. They're arbitrary symbols as long as they don't conflict. Right? Meaning I can't say x here. What will be the meaning of me to say x? That is, the relation relates what? X to x. I'm related to myself. So, right. So, in most cases, so that you get used to variations of notations, we, especially when we start doing the graphs, right, we will put different functions on the same plane. I'll tell you what a plane is. It's called a Cartesian plane, right? And we want to distinguish them to say which one is which, right? So if I call them the relations f and f on the graph, it will be confusing. So we are not constrained to calling them f because they are functions. We can call them g to say it's different from f. It's another function in other words. So the label itself tells us that this is an exponential. It's a different thing from a linear function. They are called relations. They relate. They relate your choice to what arithmetic produces by virtue of the operators. Here you see a multiplication and an addition at the same time, which is why you would need the Bodmer's rule. This rule. To say which one do you do first? Which operator do you do first? Well, Bodmer's tells you. You don't see brackets here. You don't see the word of, OF. You don't see the division, but you do see multiplication. So you start with the multiplication, which is right here, m times x. You perform that operation. Then you are done. The operation has produced an answer. The operation has produced the result. Then you come with addition. Then whatever you produced here, the multiplication produced, now you can add. So it's the order of operations, BODMAS. All these are operations. Brackets are operations. In fact, brackets they act as multiply. The word of acts as a multiply. The word M is a multiply. So they've got the same weight, but you start with what is in the bracket. And you do what is inside the bracket. You'll find other operators there inside the bracket. You do that. So we'll do an exercise on the simple exercise on the BODMAS rule, so that you know how to deal with it. It's really, really simple. The hard part is over. The hardest part is over, which is to see a relation. So why do we have functions in the first place? Why does mathematics have to have functions or relations? Well, for modeling, to model. All right, what is to model? Because it can mean another word. Modeling. So this is part 4. I can delete everything, right? Let me see. I wanted to say something, and for modeling real life situations. For instance, population growth, or carbon decay, or at what? Okay, fine. Let's put it like this. When you say growth, remember that you are saying addition. Literally, it means growth. But we want to know, how is my independent choice, right, growing? Oh, let's see. Okay, scratch that statement. How is the all right, let's hold fine. You see, I need space, that's why, but I don't want to delete anything. So x will be called, don't worry, we'll delete this, we'll write them again. Independent variable because it varies, it changes, right? It changes according to what? According to you. You're the one who says, I want x to be 10 billion. You're the one who says that. No one tells you what to do or what to choose. Hence, you're choosing it independent. But you can choose anything that's making it a variable. Right? Y is also a variable, but it depends on your choice. So we call it a dependent because it gets calculated by arithmetic after you've made a choice. So you make a choice, arithmetic takes over, and something to that effect. Takes order, meaning something to that effect, it does a calculation. That's the effect of your choice. The consequence. And then that which is produced by the operators, the arithmetic operators, right? We want to tie now that entire result to see how the x changes, how the y changes relative to the x, relative to your choice. What happens when you choose different values of x? What happens to y? Right? That's why y depends on your choice. This is a formal, this whole statement here is a formal definition of a function. I like this because it tells me what the independent variable is. There are other equivalent short form, right? So let's create maybe space here so that you see. Now I've got two different functions. One is called f, one is called g. Right? So to write f, you can write it f. Let's start with f. You can write it in one of two ways. Right? This is the first way, which I like, I prefer. But what I'm going to show you, sometimes I use those notations. Right? It says f is such that, remember I promised you to tell you about this symbol such that, the two dots, is such that y is equals to mx plus c. And I'm deliberately writing with one pen, one color. And I will ask you, so you see symbols here. Which symbol represents your independent choice? Is it X or M or C? That's why I don't like this notation. It makes you assume that we're talking about X. Right? Similarly, you can write G that way. Right? So I'm just using F for now. Other people, well, another notation for F, which doesn't tell you what F is. It says y of x. Now I like this because it tells me that, oh, you have not used F and G. You've literally, but y becomes ambiguous here. Right? The reason why I like it is that it tells me about the independent variable, to say, oh, this is the independent variable that you can choose independently, and you can choose anything. Remember, x is a real. So it can be 0, minus 10, minus 100, minus or 4,000, or billion, or minus billion. It can be anything you like. It's the real. It's an element of the real. Some people drop this. So there's literally like 4 ways. I was not aware, I was not counting, where they say y. Right? I use all of them, to be honest with you. Depends on the context, because they mean exactly the same thing. The one that I just deleted with y of x, this one, and this one. This one I use mainly when I explain, so that you don't lose sight of your independent variable. Explicitly, the function tells you the independent variable. Here it doesn't. It just says that there's a relation happening. F is such that it's y. And the relational symbol, so that you don't get trapped, because I'm trying to liberate you from the damage that was done by textbooks, according to Sarah Powell. Right? I can put a relational symbol here. I can say anything I want. Do you see why? That's why equal sign is one of those relational symbols. Of course, because F is a relation anyway. Now, some people call this an equation. I don't mind, because the danger is that there's a word equation and there's an equal sign. What if it's not an equal sign? What are you going to call it? Well, they would call it inequality. Let's say there's this sign. They'll call them inequalities. They're just relating. They're just saying whatever arithmetic is going to produce is going to be greater or equals to this. Whatever arithmetic is going to produce by virtue of operation. Remember, y represents that which is produced by arithmetic, meaning these operations. Now, what if I said divide by 2? And you don't see divide here. That will cause confusion, right? Until you say, no, but it's an operator. It's a divide. 4 divided by 2? Well, what do you mean? So I want to bring these operators. These are the loose ends. But as long as you don't, after this part 4, you don't forget these terminologies here. That is a relation, right? And then you say, well, I see another word, rational. What's going on here? Right. We'll explain what rational is. But so far we're explaining relation. I'm bringing in independent variable. Some people call them other things. Like for instance, the y is called the image. And the x is called the domain. What's the right? So you'll meet these terms. The domain is your area, meaning where you rule yourself, basically. You do whatever you like. It's a domain. That's why X is independent, because it depends on your choice. It's a choice. So Y depends on your choice, which is independent. The choice is an independent variable. This Y, the image, right, depends on the independent variable, which is your choice, this X. And the function tells you exactly what the independent. If I had said here, comma C, this will be another independent variable. Another. Right. Now, what is M, what is C? They're just constants. The values that you come with once, they're just constants. Once you choose it, you can't change it. M and C. You say, but you would have chosen it. Well, I can give it to you, meaning you don't have an independent choice on that. I can give you 2, and you can give yourself X, whatever value of X you want. So you're getting used now to just literally, it's like reading another book, but it's fine. Right. You get used to these concepts, but you have to use them constantly. So now, let's do other things. Given that you are exposed to terminologies and you know what's coming for you, and what is coming for you is nothing that you don't know. This was the hardest part. If you want to see, watch a video on functions, there is one on this channel, Kadika OER, which presents functions, tying them with other concepts of maths like set theory. You know, when I said X is an element of the real, I was using set theory notation. So set, and you know what, that video will tell you what a set is. Okay. This is a set, simply put. And it's defined exactly the way I've written it here. We say natural numbers are such that they are 1, 2, 3, 4, 5, 6. I'm defining a set and I'm giving it a symbol, which is capital N. It's just how mathematics chose to write it. It's their notation, it's the method, you know. Okay. Now, I want to go back. Earlier parts on this series of logarithms, I asked, when you teach a child how to count, do you explain to the child how you move from one number to the next? So those earlier series were saying, well, there are 2 ways of adding. Remember, we used the logic and we said we reached the stage where the word hlakanya became the natural way as we use it in various contexts. I'm going to meet my friends. You are using the word hlakanya. I've encountered problems. We are using the word hlakanya. Literally in Sesotho. Right. And they will mean equivalent, they will have equivalent meanings with the words that you use in English, like encounter, in that context. And we said after this, we identify this as an operator so that we can operate on numbers. We are using it in the context now of arithmetic. It's not a question of meeting friends. No, what's the difference? Because I was alone, now we are 2. But anyway, you can conceptualize about that. So let's start with the number 1. And I tell you that now you know how to use this operator. Right? But instead of coming with 1 again, I'm going to use the operator. I'm starting with this one. I'll go to the next one. By an action of adding 1 to this one. And I will repeat the same action. I will repeat it throughout, meaning I'll add 1. Right. Now I know the operator demands an answer. The operator, not the equal sign, the operator. But if I add 1 to 1, it's like me, I can do it, I can simulate it with anything. Here's 1. I come with an object. I say, this is 1. You're seeing only this object. Now I bring another 1. Now you don't see only this. You see. And I call what I don't say vocalized 2. It's no longer 1 like this. It's 2. I call this 2. And then I bring another 1, meaning I'm performing the action again. I'm performing the action. And I'm bringing it to this. That's what I mean by 2 plus 1. Now, this is what I would call 3. and I go on. I bring another one of what? Of the pen. It's nice to use stones because somebody can say, but this is a blue pen. It's a pen. A pen is a pen. But some people can say, but it makes a difference on the color. Well, let's use stones. Another one will say, okay, but that stone looks different from the other stone. Let's use slices of bread. Let's use things that are the same. I'm bringing another one of them. This is how you count. 1, 2, 3, 4. I bring another one and repeating the action throughout. You have a perfect understanding of these operators from the basis of coming with a number and adding it to itself. Now from this point, you can say, no, I want to add these guys. And so on. The 3 dots means, and so on. Right. But when you took a number and you added it to itself so many times, it led you to a this. So it becomes an operator. So we're looking at it as an operator. Rightfully as an operator. It has earned the right to be operator. And I say, I come with a number. And I'm performing an action, but with an operator multiplier. You'll say, by what? I say, well, let me choose 2. I choose simple numbers because I'm explaining concept. And I repeat the action to what is here. And I repeat the action, the same action. This time with a multiply and not the add. Well, this will give me. How do you want it? 2. This will give me 4. This will give me 8. And I can choose to add them. That's what I mean in the previous, in part 3, that this is an arithmetic service. You will be teaching, if you teach counting this way, without even saying these big words that I'm writing now. You'll essentially be teaching geometric and arithmetic sequences and series to a baby, without saying these words. And apropos, you will also be teaching simple and compound interest. Hence I ask you, do you see compound interest in the geometric or in an exponential function or exponential? Okay. I've deliberately chosen 2 here because reference is made in this video where the ancient blacks are teaching us how to multiply 2 numbers using what is called a doubling. That's what you mean by times 2. You're doubling. You're saying 2 khabedi. You're doubling. You're bringing, and then you're doubling this guy, and then you're doubling this guy. Literally, this is 4 plus 4. Literally, this is 2 plus 2 because you doubled 2. Literally, this is 1 plus 1 because you doubled it. That's what you mean by doubling. You bring the same thing again. If it's 4, which is 8, so the next one is 8 plus 8 because you're doubling. That's what you mean by 8 times 2. You're saying 8 khabedi, 8 plus 8. So these things, I'll talk about them maybe quickly, so that if you've never thought about them or they're new to you, you say, okay, I see what is happening. But I can also write this as, because I was multiplying by 2, this is 1 times 2. And then I say 1 times 2, which means this, times 2. And then I say this, 1 times 2 times 2 times 2. And then you start recognizing that familiar pattern from earlier. You say, no, this is 2 to the power 2. This is 2 to the power 3. Obviously, what? Is it obvious that this is 2 to the power 1? You would have known that the power 1 tells the base, meaning I can write this as 2. Because the exponent tells the base that I must write only one base, meaning 2 only ones. This is saying write 2, the base, twice. This is saying write 2, the base, that is. 1, 2, 3. Goes back to counting again. But you say, what about 1? Well, if you say, what about 1 at this point in time? I'll say, well, you didn't read the axioms of choice. Because if you read the axioms of choice, you would have met a thing called the existence of the unitary element. See algebra now. It's a law, it's an axiomatic law. What does it say, that law? That law says, well, any number times 1 or 1 times any number. So let me represent a number by A and say any number times 1 or 1 times any number. Do you know why these two statements, these two expressions are equivalent? You'll say it's the commutative law. You'll say, no, you swap them around. That's the commutative law. So this statement are equivalent. But whatever they are, because you are looking at the same thing, the answer is A. That's the unitary law. Any number times 1 is that number. 1 times 100 is 100. 1 times 1 is 1. That's the unitary law, the existence of a unitary element. That's why I like to point you to Zermelo. I think he states it explicitly. Okay? So you see now how what I categorize as algebra ties together. You grow up with it. You never throw algebra away. That's why I'm separating it, so that you are aware that there is algebra that you must carry throughout your life, for the rest of your life, and forever and ever. Okay. So we see the doubling actually being, which is explained here, by the way. There's also another video on the same channel which explains how they did multiplication of two numbers, like 73 times 40, using the doubling method. The doubling method, literally multiplying by 2. But if you do that, we did the doubling method. It gives me an exponential. If I do the doubling according to these guys, the ancient blacks, you see, we're pointing to the primary source. What is called the Ebers papyrus. It's a mathematical papyrus. Papyrus means paper. They were writing on a special paper. You'll know about these papers. There was paper, yes, there was. We thought paper was something of today. Written by these ancient blacks who call themselves Kemetiu, literally meaning blacks. But if you tell me that this is an exponent, I'll tell you that this is a logarithm. So I've got more questions. But did these guys know logarithms? Did these guys know exponent? Did these guys, well, they knew how to multiply. And then we just did it. And other things that you will read from the history, if you should know your history by right. But there they emerge again. We see a multiplication of the same number. And the axioms of choice help us to interpret this one. Meaning 1 times 2 is 2. Whatever this is, 1 times this is 2 to the power 2. 1 times this is 2 to the power 3. Literally. Because I'm operating on, meaning I'm saying 1 times, 1 times, 1 times, and of course 1 times 1. But let me interest you, but let me not cause confusion. But I will, let's do it. 2 to the power 0. I didn't want to do it. It's 1. But I didn't want to do it. Forget this. Now, I'll probably end with it. Now let's introduce more symbols than our operators, because we grow up with them. We're told about them from an early age. Because you can simulate it. I can bring 4 pens and I can remove 1. So what is the symbol for remove? Now the symbol for remove is this, minus, which in the Kemetiu language, Sesotho, is inta or closer. Keeper. Keep 1. Keep imali ekwameni, keep izandla. Keeper. Take out your hands from the pocket. Keep izandla. Keep izandla ekwameni. Keep imali. Take out money. Well, fortunately and or unfortunately, there's an axiom of choice, meaning you can use the operator. Now I need space. We're done with other things here. What you perceive, because you can simulate it as you've got a number and you can subtract 1 from it. Well, you can only take something that exists if it's already there. If it's not there, well, it will land you on the negative side. Did you get that statement? If I want to take out 1 from 3, does 1 contain Does 3 contain 1? Now, that's how I teach minors, right? However, algebra will tell you that. But there is a negative one. There is a number called negative, according to the laws, the axiomatic laws. There's nothing. Show me negative trees. There's no negative trees that I can see here. I can see 2 trees. I can see 2 lions. I can see 500 for that matter. Show me negative 3 lions. So the laws teach you that we can actually create negative numbers, which we call inverse numbers. Need to be exact at this point in time. But let's keep it general for now. So that I don't waste your time. Say, well, were they not there? You said X is an element of the reals. And you said you can choose negative 10,000. Was it not there? Now you're thinking like a mathematician. You see, algebra tells us that, well, we don't see them in nature. So we construct them. We say they exist. Right? But unfortunately, let me write these laws, these 2 laws, because they are fundamental if I can. We say they exist a neutral element. We start with this, which you call 0. If you think it exists, show it to me. Show me 0 trees. I want to see them. See, that's a problem. We say no, there is one. There is one. We construct it, which is an element of, in this case, we want to construct the reals, for which, all right, let's label this guy. This is a symbol for the exists. The word the exists. The exist is written exactly this way. This funny thing is the word that exists. A 0, a neutral element, we call it a neutral element. You'll see why it's neutral. Right? Which is inside the real. We say it exists. We declare that statement that it exists. There exists a neutral element of the reals, for which this statement, this line is called for which. For which. You see, symbols comes from words or a group of words. Like this, for which. For all, this symbol means for all. For all. For everything that we consider to be already in the real, such that, you remember the such that, when I take X, which is in the real, for every one of them that is in the real, then I add 0, the neutral element, I get X. Now you say X, let's go back to A, so that you don't think X is an independent. But you could have said that anyway. I'm just making a statement. I mean, if I use the word C in Chocho, can't I use it anywhere else? Okay, fine. But for now, so for everything that already exists in the real, if you add 0 to it, that neutral element must preserve what is already there. That's how now we've got 0 now. Now you can use 0. That's how 0 comes into existence. We make it exist. Axiomatic laws. Now, after this, I can say for all. Remember, this is a for all. Everything that is in the real right? For all of them. For which now there exists an inverse of what is already in there. Let's use A again. It's just a symbol, right? I'm saying there exists one. That's why I have to start with what? This time I have to start with what already is there. You see, in this case, there was no 0. Now it exists after this. I declare that it exists. Now I take what is already in the reals and I make something exist out of it to be part of the reals. Such that, how do I know? When I add, literally add, that which is already contained in the real with that which I declare to exist now, I must get 0. That's why I have to start with this law. I must make a law. 0 exists first. It's called, that's what I call mathematical reasoning. You can't say something until you declare it. If it's not there, declare it. If it's already there, use it. Here I'm using what is already there. Here I'm declaring. I can't swap these laws around. They don't make sense. Which means this statement is saying, for everything that exists, I can think of an inverse element thereof, and I'm calling it a negative of this. It's called the inverse element. Meaning, if you can think of 1,000, I can think of a negative 1,000. If you can think of 3, I can think of negative 3. Well, this is what you call negative subtraction. We are adding the inverse element. So when you say 3 minus 1, you are literally saying 3 plus minus 1. Because it exists now, because of this. Meaning there is a 1, therefore there's a minus 1. So you can add, it's a number. I say, now negative numbers are numbers now. Now I can add them. But it goes without loss of generality to say 3 minus 1. Because you can simulate it. There's 3 minus 1. And it becomes an operator minus, meaning it yields this result. Literally. So it doesn't matter whether you use it according to the law of the axiomatic law or as an operator. You're saying the same thing. This is going to be important in vectors, by the way. Vector algebra. Critically important that this understanding, if you let go of it, it's going to catch you up in vectors. You will remember me. You will remember the axiomatic laws. Now, we're done with the negative actually. Now, the problem is this. You see, if I never came with this, and I knew this, I never came, because you're saying, oh, there are negative numbers. And this law was not in existence, this law was not there. And you tell me that there is a negative number according to this law. Well, I'll give you 0 and I will ask you for its inverse. And you will say it is what? You'll say it's -0. Then you enter into a contradiction, because I cannot be my inverse. Can I? So there is another thought that people practice with. They say, no, things exist with their complementary parts. They don't see this as an inverse. They see it as a complementary part. Like a man and a woman. That there is a female and a male everywhere. There is cold and there's hot. There is darkness and light. Things exist in their complementary parts. Well, what's the complementary part of neutral? So you have to declare either way, whether you're seeing this as an inverse or a complementary, you have to declare the existence of a neutral element. It's that which doesn't change. And then, of course, there are unitary laws. The unitary law really applies to this guy. Now we're talking abstract algebra. Honestly, we're talking abstract algebra rather than just up. And it's important, abstract algebra, for other forms of mathematics called multilinear algebra, where you have to define vector spaces now. Not just vectors, but vector spaces. So for those who are in whatever, right? Me, I like connecting concepts that, well, it starts with basic algebra. So that is for your benefit. Right? Don't worry. These are loose ends. Right? We've seen the emergence of an arithmetic series just by teaching our bambinos how to count correctly and consistently. They must grow up with those notions, because you're cultivating a mathematical mind. Children don't have to wait until they reach grade 11 to do sequences and series. They can literally open their sisters and brothers, elder brothers and sisters' textbooks, because they're using textbooks, at the age of 8 and say, ha, I know this. Oh, which makes me wonder, what are you going to teach them at grade 11 if they know it at the age of 6? But anyway, now, I'm introducing now our brother here called division. Do you know why we write these 2 dots? These 2 dots. They are placeholders for numbers. You say there's a number, there's a number. Which is called in Kemetiu a ruler. Most of you already know, I don't have space, otherwise I would. I don't have space. It's division. How do you divide? Let's divide. Again, I use simple numbers. Let's do 6 divided by 2. Okay. thought this would be a shorter video, but it's not heavy loaded, right? Many people, when they divide, children that is, often they say, how many times does 2 get into 6? Get into 6. Everything is fine. I have a problem with the word get into. So listen to your words. Your words are very important. As you can see, words, symbols come from words using a natural language, English, Sesotho, whatever. How many times that? You say how many times. When you say how many times, are you talking about these times? Or are you invoking counting? Say how many times. I will not tell you what to think. I will just tell you my choice. It's not that it's correct or it's the only correct one, rather. Right? But you have to explain to me get into. What is get into? Why am I emphasizing this? Because in mathematics, you're going to come what is classed as word problems. So every word must have, or not entirely every word, not one-to-one match, but words, certain words play a key role in helping you, all of us, to identify certain symbols in arithmetic, in mathematics. Like for instance, if I say the product of 2 numbers, what am I talking about? Well, product is a word. It literally means multiply. Hence, product. But it's a word. And these are called word problems, meaning translate this statement into mathematical statements. Mathematical statements, well, we'll have to use these symbols. What else can they use? If I say the sum of 2 numbers, well, 2 numbers, okay? There's 2 numbers. What is the sum of 2 numbers? Literally, it means add. So if you've got 2 numbers, you add them. The addition of 2 numbers is the sum. That's what you call the answer. When you multiply, that's what you call, well, that's the product is called, that's what you call the answer. What about the difference? It's a word. It literally means this, minus, the difference of 2 numbers. What about divide? It's a ratio, the ratio of 2 numbers. So you have to identify those in a statement written in English or whatever language. And I can be poetic about those things and say, well, I want the ratio of the difference of 2 numbers. That's very poetic to me. So I don't know what get into is. So I don't know what to do until you tell me what get into means. You say it's divide, but I'm looking at divide. You see, when you define something, don't put that word in your definition that you are trying to define. So tell me what get into is. Or else, can I make a suggestion? Can I make a proposal? What if I rephrased your statement and say, how many 2's are in here? Maybe it means the same thing, I don't know. Because how many invoked counting? Meaning I just have to count the 2's in here, precisely in here. So I must start coming up with 2's now. There are 2's. I know how to come with 2's. I can go on with 2's forever and ever. There. I can come up with 2's. But I want to find out how many they are exactly here. Are contained inside 6. Contained. Well, all I have to do is to count them. But counting invokes addition. Remember? That's how we landed here from counting. So literally I must count. I don't know. But I'm going to count. 2 plus 2. I know the operator 2 demands 4. Plus 2 on 4. That's 6. There. I've reached my 6. I don't need the others. So there are 2 3's. But I know how to write that statement. There are 2 ha ra. That's exactly what this means. Which means this I can write it as, and this I can write it as. Well, there's my divide, if you're worried about it. There's my divide. And what do you do after this? What do you do? I'm right-handed. But I can do this with the left-handed. That's as simple as it can be. Trust me, I can't write left-handed. Let me tell you. Well, I tried. Meaning I can do this in my sleep. What you call cancellation. Which means the act of cancellation will yield only that which I didn't cancel. Right? Well, what is 6 divided by 2? According to you. I relied totally on every principle of arithmetic, mathematics in its entirety. Meaning the operators, understanding the words, counting, and everything else. Never invented anything. Remember, I asked permission to make a proposal that to rephrase the statement get into and say, how many of these 2's are inside 6? So that I invoke in my mind counting of the 2's. So I label them. Something beautiful has just happened here. I'm not sure if you're aware of it. But let's discover it together. Let's change this to 7. I think this pen is giving up on me, but 7, right? Hope you can see it. I'm still asking the same thing. How many 2's are in 7? I don't know. Literally, I don't know. I don't even want to know. All I know is what I know, which is counting. 2, 2, 2, 2, 2, 2, and so on. With a purpose, of course, because counting invokes this. Now, it tells me, and I can go on with the 2's. 2 plus 2 is 4. I know how to add. Plus 2 is 6. Plus 2 is 8. No, I don't want to know. I want to know exactly in 7. This 7 here. So I can't go on here. I can't go on. Because it will lead to 8. And I don't want to know how many are in 8 or anything. I want to know exactly in 7. But I find 6. And because I can add, I know how to get to 7. Because I can add. But there's something else that I need to add. Because I finished counting the 2's. And this number is called the remainder. I changed nothing. There's my divide, there's my 2. And I can be fancy if I like to show that I'm a mathematician. and say 2 hararu, 1, 2, 3, plus 1, divide by 2. This is the remainder. The remainder is not half. The remainder is 1. There it is. It's called the remainder theorem. And when you divide something and you discover after your countings and whatever you do that there's a remainder which does not contain 2, that doesn't contain the thing that is dividing. You see, if this was 3, there will be 2 inside 3. There's only 1 2 inside 3. But there will be a remainder 1. I'm saying if this was 3, let's do it together. Maybe you're not seeing it. Of course, I say, there are only 2 2s. Fine? But there is a remainder 3. But inside 3, there is 2. So I must write this as 2. But then there will be remainder 1 inside the 3. I'm back to the same statement. Because 3 does contain 2. What else does it contain? Of course, it contains 1 also. There it is. This is 3. Because I can add. Now this is 2 plus 2 plus 2, which is written 2 hararu. That's atisa, Papa. Plus my remainder. Just continuing. Just writing this in a short form. Now, when you divide by something, when you divide something by something, invoking counting, and you find out a normal, there's something that remains, and it's not 0. It's a number other than 0. Then it means the thing that you're dividing by is not a factor of 7. The complete theorem is called the factor and remainder theorem. You're looking at it, there it is. I'm going to reserve my complaint, but complaint about what? But if you give me, you tell me that the remainder is half. Well, let's do another thing. Let's discover it together. Let's divide by 4. And if the pen can do what it's asked to do. Let's divide by 4. So we are asking, how many 4s are in 7? I don't know. But I know how to count 4s. There's one of them. Now, if I bring another one, it will give me 8. So I can't go on. So something is remaining. And that which remains does not contain 4. There's no 4 here. So I'm done counting. And of course, 4 plus 3 is 7. There it is. So there is only 1 4. But the remainder is 3. 3. Not 0.75. 3. 0.75, you get it by dividing the remainder further. I didn't ask you to divide the remainder. I asked you what the remainder is. And the remainder is 3. There it is. Now, thanks for letting me rant about it. This is called the remainder theory. Now, let's do 8. You say, no, I can go on and say 4. But I can't go on anymore. Because I've reached my 8. You know how to add. You're counting the 4s. So this you write explicitly Mathematical is 4 habedi. And there's your divide by 4. And then you do your cancellation. But notice that you can add, do you still remember that axiom? 0. The neutral element. I'm telling you, you're going to love this. When you look at them, they're tiring. You say, I don't know what the hell they're talking about, these guys. But once you're getting used to them, they literally fix your brain. Literally, the axioms of choice, or axioms in general, algebraic rules, they literally fix your brain. They make you think proper. It's like you being born at home, and there are laws at home, right? There are laws. And sometimes you don't like those laws. No, my father tells me, or my mama tells me to go and bath before I go to sleep. He said, you can't get into that bed before you take a bath. No, she's teaching you how to be clean. Because you are playing with mud outside and everything. Who's going to wash these blankets when tomorrow? Your mom. Or you. And you get used to these laws. You're going to love taking a bath at night. But I think it takes getting used to, I suppose. Climatize, or whatever it's called. But that is 0. Now, because the remainder is 0, 4 is a factor. But guess what it did after you did cancellation? Because it's a factor form. Why is it a factor? Because the remainder is 0. This form. You cancelled, right? And then we landed here. Well, because it's a factor. Why is it a factor? Because the remainder is 0. I'm stating it according to the remainder factor theorem. Factor remainder theorem. 4 is a factor because the remainder is 0. You did your counting. You are done. And you did your fancy things here. Meaning you wrote this in a short form. It was already in a short form, but you wanted it this way. Because after that, you can do the cancellation. You see, when you've got factors, 2 times 3 times 4 times 5, and you divide by 5, you can cancel. But if this was plus 5, you can't cancel. No, you can't. You can't. You will need to find 5 here somehow. I don't know how you're going to get it. And take it out as a common factor. That's why you're doing common factors, by the way. But okay, maybe you think I'm joking. Times 4. Do you know why I'm doing this? Now that's my common factor. I'm taking it out. So what remains is 4 plus 0 times 4. Divide by 4. That's what I mean taking common factor out. What the hell just happened? Ah, this is wrong. Yo, I broke mathematics. I broke mathematics. How did I do that? No, you can't take a common factor like that. Yes, it would have been a common factor if this was plus. But that's changing the whole thing. Sorry about that. Ooh. I broke mathematics. Yeah, I see. Some people like one saying 1 is equals to 3, and they come and they don't realize they're dividing by 0. It's good exercise until you find out what is wrong. But yeah, this is changing the whole thing. This is like I'm saying there are 3 4s inside 8, which is a lie. So I can't do this. I'll have to find a better example of a common fact. Well, I could have used it here, but anyway, I'm emphasizing the 0 as the remainder. But now this is a fact. Now the beautiful thing is, if now this is a fact, it produces another fact of 8. And because 8 divided by 4 produces another fact, meaning I'm explicitly saying there is no remainder. The remainder is 0 in other words. I can literally write this statement 8 as 2 times 4 in a factorized way, because 2 is a factor. It was produced by the factor theorem, by the remainder theorem in this case. Hence factor and remainder theorem. So in general, you find the following. In general, you find the following. It says A divided by B is, or implies, or is related to a quotient plus a remainder. Now, if the remainder is 0, this will be plus 0, taking us to the neutral element, right? Axiom. Meaning it's Q. Therefore, we can write A as Q times B if R, the remainder, is 0. Meaning Q is a fact that gets produced by another fact. This is what you call long division. Exactly this. It's what you call long division. You've done long division. Now, I won't let you go until I give you an exercise to see the implications of this. I want you to do the following for me. 33 multiplied by 21. I'm talking to children now, but anyone can do this. Let's write the multiplication in red. What's the answer? While you're still thinking about it, I want you to divide this by 11. No, actually I lied. I want you to, yeah, by 11. You're done. Now divide it by 77. Are you done? You should be done by now. How much time do you need? Can I interest you in this before you get done? Factorize every number. Every number that you see, factorize it. You will write this as 11 times 3. Isn't it? That's 33. There's a multiply. U, meaning I'm doing factor theorem and remainder theorem at the same time, just by multiplication. This will be 7 times 3. Right. If you read your laws, you would have found another one called associative law, meaning you can multiply this 7 by this 11 across the multiplication, which will give you 77. Meaning you will have 77 times 3 times 3. I'm just using the same color, but I could have written this as red, probably that times 3. But I'm dividing by 77. And then you do the famous thing, and your answer is 3 times 3. That's how fast you can be if you factorize. Meaning multiply. Find two numbers that which when you multiply, they give you that number. You are doing long division using. If you're not comfortable with that, well, let's go back to 6 divided by 2 and interest you into the final thing. I know I'm going fast because I've exceeded an hour. 6 divided by 2, I can also write it as, well, you see, I can bring the unitary law. But then I realized that, oh, okay, this is half times 6. Now the division is gone. And this will be equivalent. This will be equivalent to half plus half. Remember, 1, 2, 3, 4, 5, 6. Half plus half, that's 1. Well, if it's 1, so is this. And 1 plus 1 plus 1. Well, what's 6 divided by 2? What have I done? I've just explained division in terms of multiplication. Meaning, division can be explained by multiplication, but multiplication can be explained by addition. And we saw, according to the inverse law, that the subtraction can be, everything comes into plus. Everything. Others know not directly, but they do come here. Rogers, 2025. There's a paper there. Those are loose ends. I thought I would take less time, but those are loose ends. Loose ends so that we can bring other operators in. But see, it gets longer because I have to point you to axioms of choice, that these things don't come from thin air. They come by declaration, because that's how nature does things. There is no negative tree. What is it? Unless if you say it's a female tree. Well, how do you know? Show me a negative female. Show me a female tree. Show me. Well, sometimes you can see a female lion, female what. That's fine. But strictly on what mathematics talks about as the inverse. Well, show me a negative tree. Show me a negative light. Show me a negative me. Good thinking. Maybe because you're thinking about the mirror. Yeah. But he's not looking there. If I'm looking there, I'm the one looking there. If you say I must put a mirror, that guy on the other side is not looking where I'm looking. He's looking somewhere there. He can see these things that are behind me. I can see them. I'm looking there. I can see a window. I can see trees outside. I don't see what is behind me. He can see it. I know he can see it. So if that's what you call a negative me, well done. But he's looking the other way. He's the negative of me. I'm not the negative of myself. Otherwise, I'll be zero. Or am I? Maybe I am. So we play with these arguments just to train the mind to falsify something. You see, it's a process of trying to falsify. You have to go through a falsification process. We try to falsify, to say, I don't want to think it like that. I want to think it like this, and then it leads you into another, like I tried to do here. But yeah, then, but we're done with the nitty-gritties of explaining, and emphasis also on, and you've seen other notation, the algebraic notation for all that exists, such that element, whatever the case may be, and logical reasoning, which is mathematical, because it tells us what the neutral element is, how the inverse element comes into play. Well, tomorrow we're going to have a function, and I'm going to ask you for this. Meaning I give you a function, say 2x plus 3. Now m and c are specific here. I can't change them anymore, but you can change x. Now f of minus x means I must use this f to come up with 2, where I see x, I put minus x plus 3. So this gives me negative 2x plus 3. This expression is different from this expression because there's a negative 2. This one is positive 2. Meaning if you draw a line, right, this other one is going to be like that. So what do you call this line? What do you call this? Relative to this, what do you call this? The inverse. Well, part 5, we're going to talk about the inverse functions. Right? Well done, guys. Thanks for your kind attention. To listen to me, wow. I have to be grateful. I want you to be the best. I really want it.